Hi there. Let's look at nucleophilic substitution reactions. So there are two models, two mechanisms we will be talking about. SN2 first, and then once we're done that, we will do the review session on it, and then we will go to the SN1 mechanism. So that's the second model, but we just swapped that one for clarity and for it's easier to understand SN2 first, and it will be logical, right? So, and we from your word cloud and the recorded lecture, and you should know by now with the text, using the text, and you should know now what's a nucleophile. And the nucleophile is a Lewis base, and then that will be donating electrons to make a bond with carbon mostly. And the nucleophilicity versus basicity, we will be talking about that later. And also we need to know a little bit about the periodic trend for the nucleophilicity. What are the strong nucleophiles and the weak nucleophiles, and the resonance effect for the nucleophilicity, and also the steric effect for it, that what's the size of it and how it can reach to its target, right? We need to talk about the electrophile, the E+. That's also the carbon, actually, the substrate carbon, and that's also we need to look at the steric hindrance of the electrophile, the nature of primary, secondary, tertiary, how many groups are attached to that carbon. And we also want to look at carbocation stability, not really with the SN2, but it will be later, but it's a really important topic to understand both of them, actually, knowing about the carbocation stability and the changes can happen to the carbocation. So that's only happening in the one, though, SN1. Now, leaving group is attached to the electrophile. That's, as it says, leaving group, it leaves, right? And then we're going to look at the reduced specificity of the SN1 and allelic electrophiles, and SN1, SN2, predicting the mechanisms. We're going to prepare the tables. We're going to have a flow chart to how to identify when you're given some information to figure out, is it a SN1, is it a SN2? How do we decide? What's the order? What's the criteria? So we will figure out an easy way, a couple of easy ways for you to work on problems for midterms and exams, right? And this part for the people who are coming from the biological stream, and this one for the people who are taking the lab. So we will do two different labs, right? Okay, so the biological importance of stereochemistry, and then it's generated, you will see some ambiguity, and also you will see very specific reaction that we can create specific stereospecific molecules as well. Now from there we're going to look at the big picture, right? So like I said, we will be talking about the strength of the nucleophile, the stability of the electrophile, and the quality of the leaving group, and we will be ranking all of them, actually, for the reactivity, for the stability, and why it's important for ranking. And then we will be talking about the carbocation intermediate stability, and depending on their structure, this is actually linked to the SN1, but it's important to understand to both models, both mechanisms, to know about the carbocation. And then the transition state is very specifically, we are talking about in the SN2, but it is existing in both cases. It can be debate in the both cases, but this is specifically, we want to look at the SN2, and we can't really touch, we cannot really isolate the transition state, but the carbocation possible. Now SN2, so we will be so you already have done your the word cloud, and you had the idea about it. You searched about the words and the meanings and the definitions of them. You have a rough idea on it, and then we're going to make a class version summary today, and together with the large group, and then we will be doing our in-class questions. We will be doing the clicker questions, and also MCQ structured essays and essay questions, right? So we're going to make a table and how to differentiate between the SN1 and SN2, and also further we can elaborate into eliminations as well, and additions and eliminations. So substitution reactions mechanism animations. Yes, there are a few hyperlinks that I will put, one or two nice mechanisms, animations that you can see rather than spending 15 minutes. So you can see it in 3 minutes, right? Now, first, so look at here. So we let me identify each group. So nucleophile, easy to identify. There is a negative charge. That's why it likes the nucleus. Nucleophile, nucleus loving. And it's a Lewis base. You can see the pair of electrons ready to give to make a bond to the carbon, right? Now this carbon, look at here, the carbon here attached to the Cl. Cl is electronegative, and that means this bond is more polarized into the chlorine, generating a delta plus on the carbon. That's why we call the carbon electrophile the E plus, right? And the chlorine the leaving group. So this whole thing is the substrate, that's a leaving group. So we have the three pieces that we need to talk about that. And then what happens here, attacks and it kicks out here and removes here, and you get the chlorine left because it's leaving group. And then you make the product here, OH is attached. So you make an alcohol, methanol in this case, right? So that's the simplest way to look at it. Now, this reaction happens in one step, and it's a concerted because bond forming and bond breaking happens at once. So let's see another thing. So if I want to get more of this product, what should I do? I need to increase this amount. I need to increase this amount, right? Because you need to put both the bricks and cement both in order to build the wall, right? So you need both of them. So therefore, that's what's happening bimolecularly, right? So the rate has to be explained with bimolecularly. Now, let's see what's the backside attack. So let's look at here. Here's the leaving group, and here's the nucleophile incoming. And then if this happens, what happens is this is a larger group. There's a large electron cloud. Here is a large electron cloud, right? Negative charge perhaps. And if it's a Nu minus, right? Now these don't like each other because they have large electron clouds. They are relatively negative. They will not like each other. And also sterically, this is larger. It's blocking. Now what's the alternative? This can go around here. That's the backside attack. That's what's happening here. See, the backside attack happens here and it leaves. So we learn about the simultaneous, the concerted reaction, and this is the backside attack, right? And another thing you can see here, if you can see here, what could happen when this happens, the umbrella should flip because this is a larger group. This becomes empty here, this side. So therefore you push here, these ones should be pushing backward. So it's kind of like here is the nucleophile coming in, that's the gusty wind, and here's the umbrella perfectly okay. Now it's flipped because of that. So that's, it's a good analogy to think of that way. So let's look at here. Now the next thing is still talking about the transition state. Let's see here, nucleophile incoming, and then the chlorine leaving group, and you're gonna go into here is the bond forming, here's the bond breaking, and then it's a transition state. So this is not an intermediate. We don't call this one intermediate. This is a 5-valent species symbolized with the double dagger and the parenthesis, and that's how the transition state. So this one goes into the product, and this is one step actually, right? So this is the product, and this is already the leaving group. It's a octet full shell. It's pretty happy here, right? Okay, so we can talk about the energy, free energy. We could talk about potential energy. We could talk about the enthalpy, but the sense of energy here is, look at the reactant here and look at the product here. In this case, it's a more stable product. It could be here too, right? But more importantly, the one step here, the rate determining step, the slowest step, the only step, and that's the transition state. So this here is the, if you remember, activation energy should be from here to here. So it should be the only step in this case, right? Now, another really important part that I mentioned, biologically important, super important one, the chiral inversion, right? So what happens here? So I have the backside attack from the nucleophile, the chlorine leaving group goes away, and yeah, typical transition stayed, and we get the product. Now look at the magic here. S is marked here, R is marked here. Let's see whether it's true. So the CIP rules you learned, so you hold the, let's give the priority, and based on the atomic number, number 1 priority, number 2 for the tritium, number 3 for the deuterium, last number 4 for the hydrogen. So it's a 1, 2, 3, and the hydrogen holding away from us, it's back to the inside the screen. So 1, 2, 3, it's counterclockwise, it should be S the sinister, right? So that's true. Okay, then we can also look at here. So 1, 2, 3, it's clockwise, and hydrogen in the back, it's an R. So that's true. But did we get that way? Yes, because see, here's the umbrella flip can happen here. It hits here, and the hydrogen is the smaller one, can be pushed, and that's pushed here. The other ones are almost where they were, right? So you can see the so inversion, that's the chiral inversion. It can happen in the SN2, or it happens in the SN2. That's the importance. But is there a way to avoid that? Think about that. Think about the enzymes. Think about the biological importance of not having the wrong configuration, like I mentioned in the thalidomide. Now, yes, so SN1, we are not going to talk about it now, and we will be going into the large group review session, and then we will come up with a one-page summary sheet, as you call the cheat sheet, and we'll make the cheat sheet. We will discuss the MCQs, their structured essays, and the essays, right? Once we have done that, and we are ready to do challenger questions, even problems you have to go for the summer research projects. Thank you.